Yeah, now YouTube is also ready, and three of them as a co-host.
Okay, thank you so much.
Yeah, fine.
Good morning and welcome everybody to today's session of Indian webinar series, Introduction to Computational Drug Design. It is co-organized by Schrödinger PCI. I would like to take a moment to thank all our collaborators for making this event possible. Also would like to thank the IT team of JSS and Manipal for hosting these sessions. For today's session, we have two talks. Virtual screening to prioritizing the molecules by Dr. Prajwal and need for flexible docking and covalent docking by Dr. Vinod. So during this course or presentation, if you have any questions, feel free to drop your queries into the comment section or the chat section of the YouTube video, and we will get them added to our questions. So with further ado, I would like to pass on the controls to Dr. Prajwal.
Yeah, thank you very much, Shalviya. So I just share the screen first. Okay, so can you please confirm whether screen is visible?
Yes, your screen is visible and we can also hear you fine.
Okay, that's great. So thank you very much. So without wasting further time, we can start the presentation and start discussing about the today's topic. So before going further, so very good morning to all of you. And again, thank you for joining today's session. So I would say today it's a very interesting session to know more on how to prioritize hits out of your library of ligands which you are using it for virtual screening. So I'll be mostly talking about the docking based whenever you perform docking based virtual screening, and then which are the criterias which that you can use for the prioritizing hits, and what are the filters which you can apply, and not only the name of filters like how to apply it, but I'll also focus on the thing which options are available with us and whether these are easy to use or it's a complicated, or how much manual intervention you need to have uh, for such filters. So please be with us, and I'm sure at the end you will find it like easy to use all those tools, and you will see like how easy it is to perform prioritization of your heats. So again, before starting that, I would like to mention here is my email ID and phone number if you want to contact for further queries if you have. So let's start the things. So just to brush up whatever we have learned so far. So computer-aided drug designing or computer-aided virtual screening is all about finding a best key. As I every time I mention about the lock and key model, and our aim is to find that best key out of all available keys in the world. So we can find it out. The chances of find it out is always better when we have efficient tools or if you do things smartly. So for that you have huge number of keys available in the world, like in various small molecule databases like zinc, pubchem, or many more databases, and you need to perform various computer aided drug designing methods to identify the best key amongst all. So as explained by Dr. Pritesh yesterday, so we are mostly focusing on the methodology called molecular docking, which is a structure-based methodology and is a part of computer-aided drug designing methodologies out of several methodologies. So there are many others, even which includes ligand-based method that we will see in our consecutive sessions. But here we will, in continuation of yesterday's lecture by Dr. Pritesh, we will focus mostly on molecular docking based virtual screening. So whenever the word comes molecular docking, so what it is, so it is nothing but just to analyze how a receptor, which is your biological molecule, how it binds to the ligand molecule, and ligand can be your key, and the whole idea is to find out the best fit of ligand molecule inside the receptor. So getting information about that complex, its energetics, the process is called as molecular docking. So there are many things which one can expect from molecular docking. Like first of all, you get the binding mode of any ligand molecule inside the protein or receptor, and we can use this methodology for identification of heat or lead compound which can have perfect fit, and we can also correlate with the potency values based on the scores or energetics which you get it from molecular docking pose. So it gives you ultimately the various conformation of ligands after docking, and based on scorings, based on interactions or various criterias, we can select the best out of all. So again, this is the brush up of yesterday's lecture by Dr. Pritesh. So what we are trying to do here is we are trying to perform molecular docking to identify the binding poses of various ligand inside the protein structure. So inside the protein structure means the binding pocket. So molecular docking algorithm predicts various binding poses of huge number of ligands, and once you will have all those ligands docked inside the protein structure individually, you will have some scores for each ligand, and based on score, which is docking score, we think we prioritize one molecule which is our best fit, and furthermore we can proceed for the substitution on this particular selected heat molecule. So minor substitution that could increase the binding of new ligand inside the protein structure, and this is the way we prioritize that particular heat molecule amongst the complete database. So as again as explained by Dr. Pritesh in detail, so in general molecular docking protocol follows you must have a protein structure with you, which you can get it from protein data bank, or you can get it from homology modeling or from any other source. Prior to proceeding for any type of computer aided drug designing studies, you need to prepare that protein structure to add many of parameters which are missing in the experimental structure, and for that we have a tool called protein preparation wizard. So same thing, once you prepare the protein structure, you need to specify the binding site. As I explained yesterday, you can have a co-crystallized ligand as a reference for the binding point, binding pocket, or you can specify few residues which you think which are present in the binding pocket. You can use sitemap tool to analyze it. So once you are sure about binding pocket, you need to go for a receptor grid generation. And so this is what you need to do it for the protein structure. So same thing you need to do it for ligand. So ligand molecules you can get it from various available databases like PubChem, Zinc, or NCI or Drug Bank. So or if you don't want to go with such databases, you also have an option to create your own library of compounds based on your requirement. And once you will have library, you need to go for ligand preparation. So for that we have a module called lig prep. So once your protein is ready, grid is ready, and ligands are ready, you can set the molecular docking parameters and simply run the docking. So these are the steps involved in it. And once docking gets finished, you need to analyze those results. So this part comes tricky. So you need to analyze your results critically and in very thorough manner. But at this point you don't need to worry about it, because in Schrodinger you will have very much user friendly tool to do analysis in just one click. So we will see that how it works. So in the general theory of how molecular docking works or how to prioritize heat, so most of the theory part was already explained by Dr. Pritesh yesterday, and you know how glide works and how it performs conformational search, or how it assigns scores, which are the parameters involved in scores. So we'll just brush up those things and we'll try to see what are the steps involved in it. So I'll not go into much detail, but overall you can categorize the process of specific molecular docking in three parts. First one is the docking, where it automatically generates conformation and try to place molecule inside the binding pocket. And third step is your second step is your scoring. So it assigns scores for each pose of each ligand, and then we can apply various filters. So in the process of docking, which is the first step of complete molecular docking exercise, is you have a ligand molecule and there is a conformational sampling method as explained by Dr. Pritesh. So it tries to generate various conformations. You can see like you have started a particular shape of ligand, and then the software explored various conformations to generate various shapes by using conformational sampling method. And then it perform docking of each ligand, each conformation inside the receptor, and then you will get the pose of each conformation. So you can see here you get a different pose for different conformation of the same ligand. So after that software assigns some scores to for each poses. So you can see there are various poses, and visually also you can see like which pose is favorable, which pose is non favorable. But we need so in high throughput manner we need some scoring functions to prioritize it, because it is not really feasible to look for each and every pose in case of lacks of compound. So for that we have a scoring which gives you the best quantitative way of analyzing results. So you can see software has assigned various scores to the ligand molecules which are present inside the protein structure, and you can see these scores are in negative. So more the negative value is, better the score is. And once you get the scores for it, you can see as I said, more the negative value, better the docking score is. So you can see this particular ligand molecule which is having highest score is kind of better. But this is one of the criteria to choose it. But not only that, we can also have another criteria which we will see. But before proceeding that thing, we need to understand the things of docking scoring methods. So basically those scoring methods are developed to give a good enrichment against the whole database. Good enrichment means nothing but it helps you to separate good compounds from the bad compounds. So that just a separation which docking the scoring methods gives you. So you can think of any software, any scoring method, if it is able to separate good molecules from the bad molecules, then we can say that scoring method is good enough. So this is what is very true in case of glide docking, and I will explain you in consecutive slides. So that's the thing. And means scoring is basically made up for a good enrichment. It allows you to separate good from bad, and then it doesn't exactly correlate with the biological activity values in general. But for example, if you think like your docking score is not correlating with the experimental values which are reported, and I would say that condition is perfectly fine, because those scores are not made up for correlating with the biological values. But if it correlates, that's well and good. If it is not correlating, then you don't need to worry about it, because these are not made up for correlations. So this is what in detail about scoring methods. And then when we proceed for the filtering, so as I said, the for filtering you can choose a docking score as a filtering criteria, but that is just a one filtering criteria, but there can be more. So here for example, I have a filtering criteria of a particular interaction, a particular contact. So it means, for example, until and unless ligand made contact with the receptor at this particular point, I will not consider it as a good ligand. So what I will do is, along with the docking score, I will also check the poses and see which pose is making interaction with this particular point. And I find that this particular shape of ligand which is docked inside the protein structure is making interaction, and the same interaction is absent in other ligands except this. So I will compare these two poses and I will see which score is better for this. So in this way, there can be two criteria. One is score based criteria, one is interaction based criteria. But again, you need to remember one thing: whenever we talk about interaction, you need to manually see each and every pose to see whether interaction is happening or not. But don't worry, at this stage, even there are lacks of compound, you will have easy to use tool which gives you all interaction profile in just one go. We will see it in a consecutive slide. So as yesterday Pritesh explained about docking algorithms, and there are three types of docking algorithms which we have in the glide, in the Schrodinger, which is high throughput virtual screening algorithm, which is fastest algorithm, which docks a ligand molecule inside the protein cavity in just 1 to 2 seconds. And then there is a standard precision, means the precision of molecular docking gets increased, but speed become less than the high throughput virtual screening method, and that less is around 10 to 20 seconds for each ligand. Then if you go for further precision, you will have extra precision docking algorithm, which would take 2 to 3 minutes for each ligand to be docked inside the protein structure. So that's very again, even if you think of comparing with other available softwares, these numbers are really less, because other softwares might take a time of 5 to 10 minutes for each ligand to dock, and even the highest precision with the most reliability, we have just 1 to 2 minutes for each ligand. But if you are dealing with millions of compound, high throughput virtual screening is the best method to screen all those ligand. We just take 1 second to dock a molecule. So just remember these things. We have three different algorithms for different speed and different accuracies, and how to use it, we will see that thing in next slides. So this is what is the docking algorithm. But as I already explained day before yesterday, there are various databases which you can use it for your ligand library, like binding database, pubchem, or zinc, drug bank, or even if you are dealing with natural products, so there are many natural product databases that you can use it for your virtual screening. So means the databases are already available, you can just go there and download it and you can use it for further screening. So whenever you have database, as I already explained, there is a ligand preparation tool which we have, which prepares ligand for you, which can apply various filters on it. We have explained those filters in detail day before yesterday. And then means it is just a single click exercise. You just need to open the panel, provide your ligand files, which can be in GBs or which can be which can have millions of compound, and that's it. Click on run, and this is just a single click exercise. It will give you the outcome of prepared ligand files. So, and the same thing is applied for the protein case. Whenever you have protein structure, you need to go to protein preparation wizard, and that just 3 clicks exercise as explained by Dr. Pritesh. Like you just need to open the panel, you need to click 3 times on the panel, and that's it. Your protein preparation is done. It will take care of everything by default automatically. You don't need to worry about your protein structure at the end. Once your protein is foolproof, you will have single click grid generation panel. You just need to open the panel, and I already explained how to pick the molecule. It is just single click. You need to click on your reference molecule, or you can get the results from sitemap, and it will perform grid generation for you. Once your grid is prepared, now you are ready for the molecular docking exercise. For that, we have just a 3-click option. You just need to open this glide docking panel, provide your grid file, which is in zip format, provide your ligand file, which you get it from the ligand preparation exercise, and select your precision method, which precision you want to go for, and that's it. It will take everything, and you need to click on run. So one of the additional option which you can have, so you can also have option for macro. If you are dealing with macrocyclic compounds or natural products or such a big compounds, you can have very specialized sampling methods which also take care of macrocyclic type of complex compounds in it. So you can perform, you can just on this option and it will take care automatically. You can also perform protein peptide docking in case if you are working on peptides or peptidomimetic compounds. So that is also being taken care of. So that's what is the docking exercise, is just 3 clicks away from you. Once you get this docking done, you need to analyze it. As I said, analysis is the most critical part of any methodology in molecular modeling or in computer aided drug designing. So but to make your life easy, we have a single click button analysis which is present with Schrodinger. Like in just 1 click, it will give you the pose of ligand, all interactions are being highlighted. The ligand molecule is highlighted in ball stick view, and amino acid residues which are interacting with ligand are shown in lines view. You will have cartoons view of protein structure, and all interactions like hydrogen bond interaction, pi stacking interactions, all are being highlighted in different colors, and you can see everything in the 3D in just best possible way. So in this way, in just you just need to load pose, click on the button, and it will show you everything. You can analyze it by rotating your molecule or translating it. It is a simple mouse operations you need to do. And if you feel like it is good to analyze it in 3D, that's well and good. But if you at some point if you feel it is messy and I could not able to find exact interaction, exact amino acid residues in this 3D view, so don't need to worry about it. We will have next button in which it gives you the all type of interactions in 2D. So you will have 2D structure of ligand molecules and surrounding amino acid residues which are mentioned around the ligand, and not only that but also interactions, hydrogen bonding interactions, or many other type of interactions are being highlighted in straightforward manner. So easily one can see it in a 3D. You can note down those interactions, and you can see whether it follows the criteria of your filtering criteria of particular interactions. So you can go through number of ligand poses one by one and see whether it gives you those type of interactions which is basically your filtering criteria, and you can select those hits as your hit molecules. So not only that, but that is what was the qualitative way of analyzing it, means just by looking the molecular docking pose in 3D or in 2D, noting down the interactions. All that method is called as qualitative way of analyzing it. But it also gives you score, as I said, which is called as docking score, and based on docking score you get that score in the project table. So that projectable button is also will be in front of you in Schrodinger. In just one click, it will give you all that scoring information for each and every pose for the ligand molecule, and based on the score, you can decide which molecules are better. So for example, as I already said, better more the negative value, better the score is. So here in this particular docking exercise, I have performed docking inside the protein called 2p33, and I have prepared first that protein and then perform molecular docking of all those ligands inside the protein structure. Not only other ligands, but I also perform the docking of co-crystallized ligand inside it. I have extracted that ligand and I have redocked that molecule inside the protein structure. And so why do I need to do that redocking of the co-crystallized ligand? Because that ligand is the reference ligand molecule for my virtual screening exercise. So what I would do, so whatever docking score I get it for the co-crystallized ligand, means our reference compound, that value is the reference value for me. So whatever is better than docking score better than co-crystallized ligand is the more possible more better binder for my protein structure. So in this exercise I will see like molecular docking score of co-crystallized ligand, which is here 2p33 ligand 2, is having minus 10.3. And if you look into other design compound which are mentioned in the list, are having score of minus 9.0, minus 8.5, minus 8.1. In this way scores started decreasing. So it means none of the ligand is having better binding than the existing co-crystallized ligand inside this particular protein structure. So it means I could not select any of the ligand for my further molecular modeling exercise. So what I would do, because I did not get better score than the reference compound, I would again redesign my ligands and again perform molecular docking of those ligands, and I will see whether the score gets increased or not. And again, you know how to perform the designing of new molecules using library enumeration tool, using bioisoster replacement, using reaction based enumeration tool. So there are many such. So that's what the maybe there can be a case when means every time you need to have a reference molecule for the comparison of your docking score for other ligands, but there can be a case when you don't have reference ligand present in the protein structure. In that case, basically you will have a chance to look into literature and see if any, though there is no co-crystallized ligand present inside the protein structure, but whether there is any drug molecule reported for this particular structure, or whether there is any active molecule reported in the literature for which nobody has performed experiments on such molecules. Is there can be many protein targets for which were explored by a medicinal chemist, but nobody has performed molecular docking against it, nobody has performed crystallization experiments on it. So such things can happen. So in such cases you will not have reference ligand, but if you have information about bioactive molecule which has some activity in nanomolar range, and which is reported by experimentalists like medicinal chemists, and then you can use that molecule as your reference molecule. And even if you don't have any such thing reported in the literature nowhere else, then what you can do is you can whatever molecules you get it from the molecular docking exercise, whatever scores you get it from the molecular docking exercise, you can simply rely on the scores and you can select, let's say, top 10% or top 1% amongst the all hit. So in this case, for example, imagine if I would not have this 2p33 ligand structure present with me, what I would do, I would simply select okay, the molecule which I got is having score -9 is my top hit, and I'll take top 10% of compound amongst my library and I'll use it for further virtual screening. If I have co-crystallized ligand present with me, I would choose whatever ligands are having better score than the co-crystallized ligand, and I'll choose it for the further virtual screening. So this is the way how we prioritize molecules. And other filtering criteria can be the interactions. if you have specific interaction which you think is very critical and reported in literature, you can make it as a filtering criteria. So in this way you can play around with docking score and interaction criteria and decide which ligand you can take it for further screening. So this is what we which you get it from the scores and interactions, but going one step further, we have uh, extra precision molecular docking algorithm which has something additional in it, as explained by Dr. Pritesh yesterday. So extra precision docking is one of the very peculiar characteristics which is present with the only Schrodinger, and it not only gives you what are the good things present between your protein and ligand. So you can see here in XP visualizer, so it's specific panel called XP visualizer. Whenever you perform extra precision docking, you will have this type of analysis which you can get it from XP visualizer. So all of the ligand molecule and all of the good features which are explained here in the blue color are all those good things, means good interactions, good hydrogen bonding, good hydrophobic packing, all those good things are present. So most of the software support good things, but research is not only about knowing good things, it is also about knowing bad things, because whenever bad things are present, whenever you come to know about bad things, you will have opportunity to improve those bad things. And this is what XP visualizer assist you in analyzing bad things. So it also gives you all that information which are badly present inside your protein and ligand contact. So whether there are various type of penalties, for example hydrogen bond penalty or exposure penalty or rotatable bond penalty, so there are many such penalties which software assigns to each docking pose if it is there, and based on that penalties it tells you like which particular ligand has particular this penalty. So if there is a penalty, then you need to critically look into that particular penalty thing, that about, for example, if you consider this exposure penalty and it says for this particular ligand 689972 has a zero point 0.7 penalty, which is exposure penalty, so it means which fragment of your ligand is responsible for this penalty. So if it is there, then in your further molecular designing you need to remove that part of ligand, or you need to modify that part of ligand to reduce this penalty values. As you reduce these penalty values, it will automatically increase the docking score and gives you the better molecule out of it. So this is what step by step you need to understand the things, you need to analyze the things critically, and you need to proceed for further ligand designing. So always remember, don't ever always go for good things, try to look for bad things which are present in the molecules. So if you remove those bad characteristics, you will automatically get a better molecule out of it. So whenever I say good parameters, like I have already explained, there can be various hydrophobic packing for the ligand molecule, which you can see here. This particular ligand molecule is packed very better inside the binding pocket. This is what is the good characteristic, which is our hydrophobic enclosure. And there can be hydrophobically packed hydrogen bonding, means a same residue which is responsible for hydrophobic interaction, but the part of that same residue is also making hydrogen bonding interaction with the ligand molecule. So those are the things, I would say those are really good things which helps the molecule to fit inside the binding pocket. Not only fits inside the binding pocket, but also stays there for long time with better binding energy and better score. So these are the kind of good things which you always have with you if you go for the analysis through extra precision visualizer. So not as I said, not only that, but you will have different type of penalties like hydrogen bond penalty, exposure penalty, rotatable bond penalty, epic state penalty. So those penalties will help you to identify bad things, and we will see in next how which are those bad things. So in extra precision visualizer, it will also show you these values. For example, this is particular burial penalty for the polar group. So you can see here I have shown in a yellow arrow that this particular part of ligand which is having nitrogen group is already polar in nature, and if such a polar group is buried inside the protein structure and it is not making any hydrogen bonding interaction or any contact, polar contact with the surrounding amino acid residues, then it will assign some penalty. Software will assign some penalty to such buried group, so that you need to understand this functional group is not making good contact, good polar contact with the residue, means it is of no use at this position. So what you will do, you will try to modify this particular polar functional group to something which is non-polar, which can make non-polar contact, because there is no polar environment present inside the this particular microenvironment in the protein structure. This is what we learn from the extra precision docking. So same thing can be applied to the solvent exposure penalties for hydrophobic group. So as Dr. Pritesh yesterday explained, whenever there is a hydrophobic group, for example this aliphatic carbon chain, if it is not making good contact with other hydrophobic group, then it means it is not stably placed inside the protein structure. So what is present here, so whenever this hydrophobic group is exposed to the solvent means somewhere outside the protein structure, whenever there is nothing, it means there is a water, means there is a solvent, and solvent is polar. So whenever it is exposed to the some polar solvent region, means in molecular docking it is exposed toward outside, and this is a aliphatic chain, means hydrophobic. So hydrophobic will not make good contacts with the polar solvent. So what then, which leads to the instability in this particular ligand pose. So software will automatically identify such hydrophobic groups which are exposed to solvent and not making good contact, means it is making bad contact. So whenever it says bad contact, means, and you will able to understand, yes, this is the group which is making bad contact, so you will have chance to modify this for particular aliphatic change to something which is polar. Either you can cut this part to make it polar, or you can substitute some hydroxyl or amino group in this particular chain to make it polar and to make good contact with the solvent. So this is what you need to understand. Same way you will have rotatable bond penalties, which says like if this is a rotatable bond and because of its rotation, or because it makes somehow constrain this rotation, because of those rotations, whether it is able to make good contacts with other amino acid residues or not. So such kind of rotatable bond penalties are also being shown. So you can think of whether to make it more flexible or whether to restrain it so that it should not rotate. So this is what the things which you understand from the extra precision docking. And as I said, while prioritizing your heat molecules, you need to think of good things as well as bad things. So if there are many such bad things present in your protein ligand pose, then you need to eliminate such ligand molecules, or you need to modify it further to make it better. So this is where you prioritize heat. And if you remember in initial slides, I'd said like if you have many such ligands present in it and you don't want to analyze each and every interaction manually, as though if you want to analyze it manually, we will have just a single click button to analyze it manually. Just load it on the workspace and see which type of interactions are present inside it, or in 2D or in 3D. But imagine you need to do the same thing for hundreds of ligand. So 100 times you need to see each and every pose. But as I said, Schrodinger is there to make your life easy, to accelerate your research work. We have a tool called interaction fingerprint analysis, in which you just need to load your molecular docking poses, even if you don't see it. And there is an option for interaction fingerprint analysis, and just a single click, it will give you the complete picture of all of your ligand poses on, let's say, y-axis, all of your ligand poses, and the amino acid residues which are interacting are mentioned on x-axis, and there are bands. So what does this bands mention? So this band says whenever there is a particular interaction is happening between this particular residue and the ligand molecule, which is on mentioned on y-axis, then it shows you the color. For example, here I have highlighted particular polar amino acid residues. So all polar amino acid residues are mentioned on the x-axis, and then these polar amino acid residues, whether it is making contact. So when we say polar amino acid residue, it mostly it will make hydrogen bonding interaction with the ligand, and whenever there is interaction present, it shows you the band. Whenever there is no interaction present, it will show you this white color region. So what it says, for example, let's take a look at this particular example, which is shown here in green color, faint green color. So amino acid, and again most important thing is it is all interactive in nature. So as you move your mouse over this particular panel, you will see all the information which is available for the ligand, for the residue, and the type of interaction. So I just moved my mouse on this particular interaction and residue. You will see on this side of the bottom of the panel, you'll see which residue it is. So basically it's aspargine 150, which is making interaction with this particular ligand name, and the structure of ligand is also shown here automatically. Not only structure of ligand, but it also shows you which atom of the ligand is making this particular polar contact. So it means, so once you move mouse on it, it will show you all type of information which is available for this ligand. And taking this as an example, you can see there is a band somewhere and there is a white color region. White color region means no interactions are present between this particular ligand and this particular residue. Then there is again band, means interaction again present with some of the ligand and no interaction with other ligands. In this way you can see in just one go that hundreds of molecule, if you load, you can see where the band is present. So now just take an example. So I'll just go back to the my interaction slide and see. For example, here this is the molecular docking pose of co-crystallized ligand, which you get it from the protein data bank, and it says like aspargine 152 interaction is very critical for any ligand to have a better binding or better biological activity. So this interaction is my reference interaction because this is very critical, which is reported in literature, which you get it from experiments. So I would particularly focus on interactions with aspargine 152 residue, and then as such manually I could check all of the 100 ligands each one by one to find out this particular interaction and the interaction with the ligand. But holistically, if you want to see, you can also see it in a interaction fingerprint analysis panel, like whether how many ligands are making such interaction with aspargine 152 ligand, and I'll pick only those ligands which are having interaction. So in just one go you can do it for hundreds and thousands of compound, and you don't really need to worry about looking at each and every pose. It will save tremendous amount of time, and this is what is very critical with the Schrodinger, and you can use it for further exercise to make your research accelerated. So finally, let's come to the complete protocol which you could follow for your virtual screening. So this is the workflow which you can implement in your virtual screening protocol. For example, you have a library of ligand molecules from any databases or enumeration. You can use that library. You can apply various filters on it, as I explained. You can go for ligand preparation, and once you prepared ligand, it is ready. The same thing you need to do for protein structure. Whatever protein structure you have, prepare that structure, prepare its grid, and test those grid whether those are good. Means it should cover all type of amino acid residue which are present in the binding pocket in such way. Once you have grid ready, you can proceed for molecular docking based virtual screening. And here you can see there is a protocol which you could follow. So for example, these are some hypothetical numbers which I have put just to give you an idea how to proceed. So for example, if you have huge number of molecules, means small molecules, means many number of ligand molecules, if you have, let's take an example of 1 lakh compounds. So whenever more number of compounds are there, like millions of compound, you need to go for high throughput virtual screening method. So you need to perform high throughput virtual screening docking against this all those molecules. Whenever you get these lakhs of molecule, you really can't see all those molecules each one by one, so we can apply simple score based filter to all those molecules. And let's say if you select top 1% of your molecules out of all, so it will end up with the 1000 molecules. So those 1000 molecules are perfectly feasible for performing a standard precision docking, because it is also faster enough, which would take just 10 to 20 seconds for each molecule to dock. So you can perform a standard precision docking on it, 1000 molecules. Then again, as the number of molecule is less, like 1000, so you can also go for cutting based on filters based on scores or based on interactions. So if there are more number of molecules, you can easily apply interaction fingerprint analysis to find out which is the interaction of your interest, and you can see the all scores. And let's say if you apply top 1% cut to all those 1000 molecules, so you will end up with, let's say, 100 molecules. And those 100 molecules are kind of feasible to perform extra precision docking, that will be more precise, so you'll get precise results out of it. So whenever these 100 molecules are with you, it is possible for you to visually inspect all those molecules for their interactions, for their pose, for their bad characteristics, for their good characteristics. And ultimately the score is also one of the thing which you can apply as a filter. And then whenever you have less molecule, you can also you can apply this filter, you can increase basically that filter, let's say 10%. So if you apply the 10% of filter, whatever molecules you think which are better, we can proceed for either further molecular mmgbsa binding free energy calculation, which for which we have a module for computation of binding free energy. So if you apply such filter, you need to do it for, let's say, 10 molecules, and out of 10, either you can stop your virtual screening process here, or you can go for molecular dynamic simulations for such compounds which you think which are good enough, based on your binding free energy profile, based on your visual inspection, based on your interactions, based on all good characteristics. So based on that, you can decide which molecules I should go further with the experimental study. So you can buy those compounds, let's say out of 10, if 5 compounds satisfy all of your criteria, you can basically buy those compounds or synthesize those compounds and test it for the further biological activity. So this is what in general virtual screening protocol which we follow for docking based virtual screening. So you can play with those numbers like top 1% or top 10%. So it's all up to you, but this is the in general protocol which you could follow. So as I said, like if you compare various software, so there is a already known study which is published in Journal of Computer Aided Molecular Design in 2012. So they have, authors have basically performed enrichment calculation using various softwares like Glide, Gold, or Doc. So they found that like Glide is performing very better in case of any other softwares also, and it gives you all good enrichment. Means it Glide docking score is always able to identify all active molecules from your data set in very good manner. Like for example, in all 100% of molecules, it almost identify 80% of active molecules amongst all, which is most in all other software. So that's why I always said Glide gives you more reliable results. So this is what we learned about this type of dockings, which includes high throughput virtual screening, standard precision, and extra precision docking algorithm that you can use it for the filtering or prioritizing your hits. We have also seen what to do in case of macrocyclic compounds. If you are dealing with, you will have option to tick. That's it. If you are dealing with peptide compounds or peptidomimetics, so you will have option for it. So this is what we have learned from this particular presentation and exercise. And in next, my colleague Vinod will take a session on covalent docking and induced fit docking, and how to perform it and why to perform it. Always in research, why to perform it is that question every researcher should ask themselves. So why to perform it, he will explain it, why, what is induced fit docking and what is covalent docking, and how to proceed further with it. So with this, I would end the presentation, and finally I would acknowledge my team who are working in Bangalore, and we are working round the clock to answer your questions, to support you in all possible ways, in scientific manner, in technical manner. So please feel free to contact us in case of any queries. So at the end, I would like to say thank you to all of you for joining us and listen the presentation carefully. And at the end, I would like to open the session for questions if you have. Thank you very much again.
Thank you, Dr. Prajwal, for the presentation. I also just found out that today is World Pharmacist Day. So I would like to wish everybody in the audience and in our panelists a happy World Pharmacist Day. So we do have time to take up a few questions. I received a few already. As a reminder, if you still have some question, you can get them added in the chat and we will take them up. So the first question, how can we select the grid size, like a different size than the default? For example, if you want to select the size at 8 angstrom or 10 angstrom or 12 angstrom, is that possible?
Yes, it is possible. So the size of grid is always depending on two things. So first of all, it should cover all the amino acid residues from the protein structure which you think that are present in the binding pocket. That's the most important criteria. You should not miss any amino acid residue out of box, grid box. And other criteria which you think of is the size of ligand. So which size of ligand you want to dock inside that particular binding pocket. So for example, if you are using, let's say, small grid size, so that small grid size is perfectly fine for small molecules. But let's say if you are dealing with macrolide compounds or natural product compounds which mostly are indeed big in size, so in that case you need to analyze your library of ligand and see what is the range of size lengthwise for your ligand molecules, and accordingly you need to play with the grid size so that it should accommodate even bigger ligand inside it. I hope it answers the question.
Yes, thank you. So we got a couple of questions on how to validate the docking results and how to avoid or weed out the false positives.
So how to validate docking results is the straightforward thing. Always, as I explained, whenever I, in that particular example, whenever I redock the co-crystallized ligand inside the binding pocket of protein, so whenever you redock the same co-crystallized ligand inside the protein structure, you need to compare it with the co-crystallized pose of the same ligand. If your docking program is able to generate the exact same pose as that of co-crystallized ligand, it validates the molecular docking algorithm. So that's the way. So to compare those poses, you can visually superimpose two poses and see if it is same, or you can also compute RMSD value for the both poses and see if it has less RMSD value like 1 to 2 angstrom. It is fine, but if it is more than that, then it doesn't look similar as that of co-crystallized light. So you need to check it by visual inspection or by RMSD values whether it able to reproduce the same pose. Yes.
Right. So there's a question, is it necessary to remove bad contacts? And is there any criteria to do that?
Yeah, so bad things are always means one need to get rid of bad things. So you need to visually inspect where are the bad things and how I can remove those bad things. For example, if there is a, as I already explained in the presentation, if there is a hydrophobic group aliphatic chain which is exposed to solvent, and because it is making bad contacts with the polar solvent, so you need to get rid of that bad things. Either you can cut that particular hydrophobic region of the molecule, or you can substitute it with some polar functional group so that it makes good contact. So there are many such strategies which you can apply, but again visual inspection is necessary and critical thinking is also necessary.
Okay, there's a question about the optimum binding energy. Is there a value to it, and is there something like a minimum cutoff, or more interestingly, is there something like a maximum cutoff to select a molecule?
Yeah, so there is no minimal or maximum cutoff for binding free energy. It all depends on case to case. So for some protein ligand complex, it might go up to, let's say if you are talking about binding free energy and specifically mmgBsa binding free energy, it might go up to minus 70 kilocalorie per mole. For some of the protein ligand case, it might go like minus 20 kilocalorie per mole. So there is no straightforward answer for it. You always need to think of reference compound. You always need to think for experimental evidence which is available and experimental values which are available. So yeah, you always need to compare it with reference.
Because there's a question about like after knowing the penalties, should we go and change the ligand groups, and should we do the docking again? Is that a right strategy?
Yes, this is the right strategy. Always remember, computer aided drug designing is all iterative process. It doesn't stop just by doing once. You need to do it hundreds of times. Probably you need to do it thousands of times. It's all iterative process.
Okay. All right. So the next question is how enrichment calculation is performed. Also, would you please explain the theory behind it?
Yes, so just need to remember one thing, enrichment calculation is all about finding the active molecules, means known active molecules amongst the database. So for example, in simpler way, you are dealing with 100 compounds. So out of 100 compounds, so you got those 100 compounds from some database, and you know those 100 compounds are not at all active. You know that thing, so we call it as a decoy set. Basically, decoy set means nothing but the molecule which looks like active just by visually, but it is not at all active. That thing we know. So what we do it, then we just take that 100 compounds which are inactive in nature. We put our known active molecules inside that database randomly. Let's say 10 molecules, you 10 active molecules you put in the complete data set, and now the whole data set will become, let's say, 90 inactive compounds and 10 active compounds. Let's imagine the number. So you will have 100 molecules in which 10 are active compounds, you know about it, and 90 are inactive compounds, that also you know about it. So what you know about it, but software doesn't know about it. So what you will do, you will dock those 100 molecules in the protein structure, and you will see the in the top 10% of it whether all of your active molecules get picked up at top rank poses. So if it is so, it means your molecular docking program is correctly picking all those active molecules. But what if it doesn't pick your active molecules, because you know software doesn't know anything. It will if software picks all inactive compounds as a top rank poses, it means it is not giving you the good enrichment. So we need to think of it. We need to play with your docking algorithm, that what is going wrong, and you need to improve that enrichment at the end. So it is all about finding active compounds amongst the data set of inactive compounds. It's called enrichment calculation. In Schrodinger, we have a simple panel to do this task, and we will see it in actual demo.
Thank you. The next question is, so when we are changing the groups on the ligand, we are also changing the property of that molecule. So do we need to check the ADMET profile of the modified molecule? How do we do that?
Yes, you need to check ADMET profile also. For that, we have a simple tool called Quick Prop. So it will calculate all those pharmacokinetic properties for you. So as I said, it is iterative process. So you need to design new molecule. You need to check for pharmacokinetic property. You need to check for perfect binding, and then you need to make a particular balance out of it. So yes, you need to do it. For that, we have tool. We will see it in consecutive lectures, what is name of tool, which is quick prop, and how to use it. It is also straightforward tool. Just open the panel and click on run. That's it. It will give you all output results.
Right. And also one of our attendees are asking, like, is it necessary to redock your native ligand?
Yes, it is necessary to compare.
Okay. So the next question is, if there is a mutation in protein, will the software take the confirmation of protein according to the mutation?
So whenever there is a mutation in protein structure, so either you will have that mutated protein structure present in protein data bank that you can use, or you can also generate a protein structure with that particular mutation, and then you can proceed for molecular docking in that protein. So software will take care of it.
Right. Also, a lot of our attendees are still confused about the co-crystallized ligand, because in some software you have to physically remove it. So they're asking, before docking, is it necessary to remove it? How to remove it?
So the simple answer is you don't need to worry about it. So software will take care of everything. Yes, I mean in case of most of the other software, you need to remove it manually. But with Schrodinger, you don't need to remove it manually. Remember, you don't need to remove it manually. Software will automatically remove it in a background, but you don't need to do these things. Software will take care of all those things. So that's what the easiness you get it with the Schrodinger. That's why Schrodinger is popular.
Right. There's also a question if you should be checking the ADME properties before or after the docking.
So the answer is it's all up to you. So there are various methodologies which are available, and how to tweak in between those methodology. It all up to you. You can perform first molecular docking and then go for ADME prediction, or you can perform first ADME prediction and then go for molecular docking. It's all up to you, and both ways are correct. There is nothing wrong in it.
What is the difference between the G score and the docking score?
So G score and docking scores are almost same except the penalty values which software assigns. So finally the docking score which you get is kind of reliable because it also includes epic state penalty in it. So you can always rely on such value which also includes penalties, not only good things. So this is what I have emphasized on. Research is not only about knowing good things, but it is also about knowing bad things, which gives you opportunity to improve. So docking score, you can consider it as a final.
Thank you. There's another question. If another ligand is present in the extended binding pocket, but your ligand of interest is only one, so how do you generate the grid around it? Do you have to consider both the ligand, or just one, the ligand of interest is enough to get the grid generated?
Yeah, so you just need to consider, you just need to specify software where is the binding pocket by just specifying one ligand of your interest, and you need to keep that another ligand inside the binding pocket because it might have some biological role. For example, in kinases, there is a ATP which is present there, and that ATP has biological role in activation of kinase. So you can keep it if you are not designing any competitive inhibitor against ATP. So you need to think of it.
Thank you. Moving on to the next question. There's a question about toxicity prediction and how can you do that through Schrodinger
So
tools.
yeah, for that we have quick prop tool as I explained, and we will see that usage of this tool in consecutive lectures.
Okay, I think you already sort of went over this question, but this question, the person says, no drug is perfect, but we only change the grooves for the sake of getting a perfect fit. Isn't it wrong to change the properties of the drugs?
Yeah, it's not wrong. In research, nothing is wrong until unless you prove your hypothesis. I would not object on it if you say something, but it's all up to you. You are the researcher who needs to think, even sometime inside the box, sometime out of the box, and it's perfectly fine.
Right. So next question is, can a pose with low glide E model energy be the pose which does not represent all the interaction? If yes, then can we select the next pose that actually represent all the, sorry, I lost the question. Okay. Then can we select the next pose that represent most of the important interactions?
Yes, simple answer is yes. It's all up to you, and there is no wrong in selecting next pose or even selecting the first pose. It's your criteria, it's you who is the deciding factor. There is no wrong in it. It's fine.
Right. So the next question is, while we are redocking the native structure, um, okay, so we get a hydrogen bond interaction that is not same as the PDB co-crystallized structure. Then what should we consider as a control?
So if you are not getting a same pose as that of co-crystallized structure, then you need to refine your grid, you need to refine your molecular docking process, that things you need to apply, or even if you don't get it, you will have option as a various constraints that also you can apply to get the exact pose. So we need to think of, so it's always about, you need to think of, if you're not getting something, you need to know why. You need to find out the answer why your molecular docking program is not able to generate the exact pose. If you are able to find the answer for why, then it will solve your research problem.
Thank you for answering those questions, and thank you everybody for submitting your questions. If you still have any more questions, and first I would like to ask our panelists, did I miss any questions? I think I got them all.
No, I don't think so. I think you got them all.
Okay, great. So yes, if you still have any question, you can write to us on ddcourse@schrodinger.com. I think we are making good time, so we can quickly go to the second session for today, the need for flexible docking and covalent docking by Dr. Vinod. I also have some announcements for you today, so please don't log off after the second presentation. Please stay tuned because we have some exciting news for you. So moving on, I would like to give my controls to Dr. Vinod. We see your chat window, the Zoom chat window. Yeah.
Okay, very good morning to everyone. Can you hear me, Shalya?
Yes, I can hear you. You just have to go
Great.
into the presentation mode. It's not showing
Thank you
yet.
very much. Thank you very much. And thank you, Prajwal, for such a nice introduction on molecular docking. So let me just place it in presentation mode and then I'll get started with it. Okay. So the topic I'm going to discuss on is need for flexible docking and covalent docking. So there is a saying with the experienced modeler, like docking is not drug discovery. There are many methods, and in many situations, we have to use different tools. My talk will purely focus on what is flexible docking, when to use it, what are the pros and cons of these methods, and what are the advanced techniques currently available in industry. Okay, so that will be my topic of discussion. just to get started, these are basic thoughts that enzyme inhibition has two kinds, like reversible, irreversible inhibitors, and many discussion until now was going on non-bonding interactions, which comes under category for reversible inhibitors, where we actually have docking, that is molecular docking or flexible docking, and irreversible inhibitor, many of the molecules are with covalent binders or covalent docking in nature. So why I have to bring this, because both of these are common grounds that I have to bring into discussion. So, but as I said, my topic will be induced fit docking or flexible docking and covalent docking. This will be my topic of concern. And to understand the science behind this, we need to get into little basics and try to understand the movement of organic atoms or amino acid atoms, residues, protein secondary structures, and so on. Already a discussion and next presentation was given by Dr. Pritesh on how the force field understands as per the knowledge on harmonic bonds or harmonic angles or dihedral angles, and then electrostatic and van der Waals contribution to understand this real-time scenario of different atoms. This all details are already contributed in the force field, and that's how you are able to see and predict this natural occurrences. And just to understand, okay, so flexibility can be provided by this laws, but what about protein flexibility? You know, protein is a big macromolecule, right? And especially theoreticians are well aware when the atoms are small, you can frame your force field parameters. But as the system goes bigger and bigger, it's very, very difficult to subject rules. I think still a topic of big concern is protein folding. And when you see this slide, like you can see in one side we have options of local flexibility, and in other side you can see a complete flexibility. So these are two techniques. The techniques names are called as flexible docking and molecular dynamics. So molecular dynamics is going to get covered later, but both of them are flexible, right? So why you need two techniques, that I will be discussing. Okay, so let me just try to explain when a protein moves, how it can move. You know, protein has structurally conserved region, that is helix and sheets, and they are well networked with the hydrogen bonds. So major deviation in a protein in a sheet or helix, that's the reason they called as structurally conserved regions. It's not possible. Okay, so you won't get major deviations. If it happens, we call it as denatured protein. But whatever changes you get in is from the loops. So loops, turns, all these are the major reason of movement. Okay, and that's the reason you have seen the movement in the earlier image in the binding site. So here there is a nice view. You can see how this catalytic domain of TNF alpha converting enzyme moves. So this is which is in, you can say, active form, inactive form, open form, closed form, all these variations of a protein. So like humans, receptor also has a hidden characteristics which need to be explored to understand about the proper drug discovery. So I think now we understood the logic of flexibility, and now I'll try to give you more details on induced fit docking. So what is induced fit docking and all that? As I already shown this slide of induced fit flexible docking and molecular dynamics. Now I'll explain what is the difference between them. And now I think many of us, especially old modelers, are aware computing resource was a huge problem for us. And whenever you need to explore the flexibility of your molecule, because docking is a guess pose, and obviously there is a possibility when it is in movement, the binding pose may not be stable, And that is the reason these high-end techniques were introduced. And during that time, performing a molecular dynamics run for a duration of say particular 1 nanosecond also was very, very challenging. In that case, flexible docking was very, very useful because it introduced the flexibility in the binding site alone. But now, due to emergence of molecular dynamics, that is GPU, and the codes are available easily and calculation runs much faster. So everybody has started using molecular dynamics. But according to me, both these approaches helps us to understand the stability of a molecule inside the binding pocket. So as you can see here, these are the changes. Now your docking pose or docking various poses can only allow flexibility in the ligand. But notice that in this world, everything is in motion, even a single atom to solar system. Okay, so everything will move, nothing will stop. So induced fit docking is a situation where the receptor changes shape and it binds to a ligand so that binding site closely confirm the shape. It's like a what you evoke a biological response of your receptor. Now, what happens? I think I earlier told in my presentation the difference between a lead and a hit molecule. So according to me, if a molecule is bound at lead stage, that is in nanomolar or picomolar stage, then I will say they are tight binders. They are relatively binding very tight. And if you notice, the various PDBs deposited in RCSB also, you can see the binding pocket doesn't stay the same. The biological conformation of a protein is when a bound ligand is able to induce a biological outcome. Okay, so those things need to be explored. And using molecular docking alone, you won't be able to do that. But yes, docking is used. The science behind is to use a combination of hybrid techniques, that is glide and prime, where we perform initial glide docking by reducing the van der Waals scaling and mutating the active site residue, that is we call it as ALA scanning. And then this complex are further refined by prime. So homology modeling and loop refinement. Prime is a very famous tool, and this is used. So this algorithm takes care of side chains and minimization. And then you try to create an induced fit scenario where at the end you need to rescore using glide. So you can see it's a combination of glide and prime. So this is another pictorial explanation here. Like you can see, this is a ligand, this is a receptor. This doesn't stays like this. And the algorithm with the reduced van der Waals scaling, and it tries to minimize the protein and the ligand, perform the redocking, and you end up getting a bound ligand. Okay, so this is quite enclosed. The pocket is exposed here. You can see it is closed. And this happens due to the movement of the loops. But you need to keep in mind, as docking, you have different modes like high throughput virtual screening mode, then you have standard precision mode, and then you have extra precision mode. For a single processor to process all these calculations, where it takes close to 20 filter glide process, it calculates the low energy complexes and best rescore the best glide score. It takes for a single complex maybe approximately close to 13.5 hours. So you can imagine the calculation which used to happen in minutes now has changed to hours. Okay, this is just a rough estimate to tell you this is computationally costly, means time consuming process even for computing. And the reason is because of all this multiple workflow that is involved in combination between glide and prime. And only our work is to validate like how well it has performed. Now I'll try to show you some validation case studies, minor internal case studies, where we have tried to like you can see, this is one Kim, the PDB ID, and this is one Ki4 PDB ID. Now this ligand is introduced in one Kim. And then when that happens, if you try to do the same using normal molecular docking, you will see that you are missing totally the binding pose. Now, some of you, I have seen many researchers, what they do is they perform molecular docking and get biased to get their interaction of choice. So it is not biasing, like generating various conformer and stopping at the pose, which is very more likely to give me positive outcome. That is not the case. And that is the only reason many of the reviewer ask for flexible docking and now more likely molecular dynamics, because any bias I do when molecular dynamic runs, it doesn't stays there. So the study does not involve to catch this interaction. The study involves to find a molecule that naturally forms this stable interaction. So that gives higher chances of identifying new molecules. Now, this is one example where the ligand RMSD, I think there were many questions on validation. So you just calculate the pose RMSD of the native to the crystal, and you get your ligand RMSD, which was redocked, and that is close to 0.4 Armstrong. If you perform the same using conventional softwares, you won't be able to achieve this outcome. So obviously you saw there is loop movements, and docking was performed twice, energy was evaluated, and then that you get your outcomes. The second calculation is like by default, the ligand RMSD we achieved was close to 7.6 Armstrong. And when you do, this is the concept of reverse docking or cross docking, which I was referring earlier also. So when we do the cross docking with IFD, we have received a close to 0.3 Armstrong deviation. Now, if you take this complex and perform MD, the ligand need to be stable and sitting here. It should not just come out. Okay, so MD needs the least energy, conformations. Okay, the initial guess state should be correct. For example, if you perform a molecular docking and try to perform molecular dynamics with a normal molecular docking pose, then the problem is you may not get a proper interaction because you have not created an induced fit scenario. The next example is with estrogen receptor, where conventionally we get close to 5.3 Armstrong, and when we perform that is cross docking, we end up getting 1 Armstrong.
Hi, Dr. Vinod, can you hear me?
Yes.
So you have your the Zoom control bar on top, and people are not able to see your topic.
Let me just find how do I. Okay. Okay, is it okay now?
Yeah.
Thank you.
You.
Yeah. So sorry, I didn't notice. Okay. So just to move forward, I was saying that estrogen receptor, and here the RMSD ligand RMSD was close to 5.3 Armstrong. And when we perform IFD calculation, we end up getting 1 Armstrong. So similarly, there were many studies that we have performed. And you can see in rigid receptor docking how the RMS deviation was too high, and whereas in induced fit docking scenario, we were getting very good poses in the initial guess state also. Please understand that it is not to find, it is to find stable interactions and stable and consistent interaction, because obviously the reviewer means, for example, now I have get high deviation. I'll try to generate so many poses, and the bottom low energy one, who is watching? So who is watching? Nobody's watching. I'll take a pose which is solvent exposed and claim that the RMSD is coming very nice. But when you perform MD studies, all the truth will come out. You will notice whether it is able to retain the critical interactions or not. So this is another comparative study where you can see how the rigid docking was relatively worse than induced fit docking. The induced fit docking always performed better because of the induced fit scenario. please keep in mind different chemical entities induce different conformation in the binding site. Think about this like I think there are apartments for renting or selling, right? The apartment, all the apartment rooms look similar, but based upon the taste and nature of the occupant, when you enter into different rooms, you will see customization in each plot. So it's the same analogy you need to apply to a receptor too. So when you see here in induced fit scenario for terphenadine bound to a hug receptor, so this is terphenadine in a normal convention. This is cisapride. You can see how these residues are able to change the conformation. Okay, you can see in serpinodol, and now the point comes like, okay, this is fine. This seems like promising. So when I have to use this, when and why I have to use it. Okay, so induced fit docking is not a luxury tool. It is need to be used very carefully, and I'll tell you different scenarios when you need to use this. Okay, so the first thing is you need to have an experimental active molecule which is not crystallized. Think about this situation. Like you have performed screening, you have identified molecules, you have done the biological activity. Out of the guessed molecules, there were 2 molecules which were highly active. And in traditional approach, you need to go and crystallize it to understand what is the interaction. But nowadays, they perform induced fit docking and they perform molecular dynamics rather than crystallization. Because the bound ligand may be of different nature, and that could be the reason. So you should not try to, okay, see my molecule is not docking and I want to do induced fit docking. That is not the case. Okay, so induced fit docking, you should literature, as per experimental facts or as per literature, you should surely know that this molecule is active and crystal structure is absent. And obviously that molecule is going to produce some induced fit scenario in the binding site. Now again, this is very famously used this with natural compounds. So natural compounds, again, see, you can't do like complete virtual screening of natural compounds, but compounds that are well known to be bound to this receptor can be tried, because natural compounds, many of the natural compounds are quite big in nature. Okay. And it is also used to explore the binding pocket flexibility. Okay, so what are the different sizes of pocket it can take, whether my ligand will be consistently available in the binding pocket. So those things it checks. Okay, so and other thing, like, you know, this is pretty famous. If your loop of concern has something called as active form, inactive form, open form, closed form, in form, out form, so that also can be explored if you correctly select the loops of your interest. And please keep in mind, it is a hit and lead optimization tool. You should use it for not for your hypothetical molecule, but actually biologically active molecule. Okay, not in silico outcomes. And IFD pose, as I already said, can be used for your molecular dynamics study. Now, and one more thing, this is very much used when you have a homology model structure. As I said, protein in bound form and unbound form has different shape and size. So via homology modeling, if you have modeled your structure and you are docking some new active molecule that you're well aware of it, or if a crystal structure doesn't has ligand bound to it, in that scenario you have to use it. And when it should not be used. So this is not for virtual screening. I think I already told this, because I have seen scenario, the students in curiosity starts using IFD and come back to me after 2 months stating I have done 1 lakh molecule induced fit docking and the job is still running. Obviously it will be running. And this is not to force dock your ligand inside the binding pocket. Please keep that in mind. And when we see the protocol, like when you notice the protocol, this is how the induced fit docking panel looks. Though I explained so many things, it is very self-explanatory, where you need to you have to browse in the demo session. I'll be showing you how to do it. And here is your centroid of your workspace ligand. In case you have it, or in case you don't have it, you can define the centroid of the residues. And other things are by default, you don't have to mention anything. Automatically it will identify the loops, and it has two modes, standard and extended mode, and all that. So as I say, Prajwal usually say, like, and it's quite easy with a single panel doing all this science in the background. So it's very easy, but I'll be showing you a demo in the second phase of our webinars. So the output, what does the output shows? It is going to give you the IFD score. The IFD score rank ordering different poses. Now, if I am in your case, I will not see, I think it is a common trend to take the top pose. Obviously, you can take top pose, but you need to perform consensus analysis. Consensus analysis, like, see, this is a figure where I have overlapped all the poses of the same ligand. I will watch out for common interactions that this pose is able to produce. If I have faked it, obviously this consistency I will not get. This is on 3D qualitative view. Quantitatively, we have this interaction plots, which were just shown by Prajwal. So we can also see in top 20 posers, what are the consistent interactions that are frequently occurring. It is about consistency, right? Obviously, we look for consistency. It is not to fake the interaction. Please keep that in mind. And very recently, we have advanced methodology. This is just for knowledge, and it is majorly used in commercial environment. So what is the advanced method you have is IFD-MD. So in IFD-MD, the original receptor conformation of the binding pocket and 3D component of the native ligand is taken into consideration. It will generate thousands of possible pharmacophoric matches between the native and cross-docking of the receptor, and the optimize the receptor side chains for each receptor match using prime, then cluster the resulting receptor conformation dock with glide. So you can see there are so many tools that are being used. That is, first I have used pharmacophore, then you can see prime, then you can see glide, and then again loop refinement. So this all phenomena was already used in IFD. But, and then what is additional in this? The additional thing that is available, the same process is done, but rank ordering of this whole thing is done using molecular dynamics. So that is the reason this tool name is called as IFD-MD. So where classical, and with it has hybrid tools, additional value of phase pharmacophore modeling, molecular dynamics, and if required water map, and all those hybrid methods are used in IFD-MD. It's computationally very costly. So, and it is only used in commercial environment. Okay, this is just for knowledge. It's fine. So you can see how the deviation of IFD-MD and normal IFD you can use. This is just for information. For your current research, you can use IFD alone. Okay. So the next topic is on covalent docking. So covalent docking has gained a lot of popularity post-COVID. I think everybody know, but if you notice, the covalent inhibitor were there. It has a history of close to 100 years. So the initial covalent binders were like aspirin, and you have very classical drugs, penicillin, omeprazole, the prodrug, and the very recent ones are approved are dacomitinib and other drugs, BTK inhibitors, and so on. So this is a very common trend now, and the science behind getting a covalent drug molecule is totally different from molecular docking. So you need a completely different tool for the same. When it comes to analysis of FDA approved drugs, the contribution of covalent drugs is, like you can see, 3% of the molecules treat inflammation, 5% cardiovascular, central nervous system, gastrointestinal, cancer, and so this is already there with us. And maybe if you watch out for recent reviews, you will get more molecules. And especially for COVID situation, there are many molecules in clinical trials now being considered. Okay, so what are the advantage and disadvantages of covalent binders? It improves the efficacy. It does the lowering of doses. So that is the reason we have anti-diabetic drug also approved. And it increases the compliance due to less frequent dosing. It reduces the possibility of drug resistance. The problem is like unexpected toxicity or hypersensitivity. Drug-induced toxicity is very common, and it should not be used for rapidly turned or degraded enzymes. Okay, and it is very tricky to find the correct warhead. So these are the advantages and disadvantages of covalent binders. A covalent bond is a chemical bond that involves the sharing of electron pairs between atoms. Shared pairs or bonding pairs has a stable balance of attractive and repulsive force between atoms when they share electrons. So that would be termed as covalent bonding. Now, for many molecules, the sharing of electrons allow each atom to attain the equivalent of a full outer shell. So that ends up in corresponding a stable electronic configuration. So this should happen inside. This should be a nature of an enzyme. Then only a covalent bond will form. So this is a small example, like where it has formed a covalent bond. So I get frequently this call stating when I'm trying to generate a grid, it is saying too many atom picks for grid generation. So that is a common error which usually reported. The reason is it is covalently bound. So how to fix it? You have to break this. You have to identify this bond, break it, and then look for. You can try molecular docking if you are interested with molecular docking. But we have a separate tool for CoDock for covalent docking. And the idea is it forms initially a non-covalent complex, and then it forms a covalent complex. I'll be showing you slides based upon that also. When it comes to covalent molecules, it is majorly available with shallow binding sites. Now, a receptor is available. A receptor has hydrophobic binding sites or druggable binding site, and there is another receptor binding site, that is shallow binding site. And please keep in mind, the covalent binding, you can't just decide one day like, okay, I will get a covalent binder for this receptor. It should have reported literature of covalent tendency of the proteins. If it doesn't have, then you can't do covalent binding with that receptor, because I have seen many research, they force the receptor. Computationally you can do, but think about in wet lab, whether it will happen. If you don't have any experimental or literature proof, performing this study will be waste of your time. So usually the warheads in your protein is hydroxyl or sulfur hydryl groups, which is majorly tyrosine, threonine, and cysteine. So these are frequently reported residues that forms covalent bond. Okay, so which is with hydroxyl group or with your sulfur, that is cysteine. Okay, and reactive warheads of the molecules. So this is also a trend. They start with virtual screening on covalent inhibitors, but the problem is you need to have reactive warheads. So you cannot have any library like normal library that you use for your virtual screening. So for covalent inhibitors, you need to have reactive warheads. So you need to have a specific library for covalent inhibition. And here are some examples. So this reactive warheads, if available, then only your docking will occur. And we need to clearly understand what is the mechanism by which this bond is forming naturally. Now, computationally, I will be able to do any adjustment, but if the literature, if it doesn't happen in the wet lab, it's not going to help. So if you see, covalent docking is a process of knowledge-based docking, where I predefine which residue it can form a covalent dock, and what are the reactive warheads, what is the mechanism going on, and then carry out this automation. Okay, so there are so many mechanisms. It involved. You need to study about your receptor, and according to that, you need to strategize your drug discovery technique. So this is not, so Schrodinger has covered major reactions, all of them, and there is options for customizing your reactions also. So if you have a custom reaction for forming a covalent bond, then it can easily be done. Now, what are the main steps? As I said, see, again, it has a combination of glide and prime. So conventional non-covalent docking by glide, and then formation of covalent bond by the different Smiles-based reaction mechanism that we defined in the CoVDoc, and then structural refinement based upon covalent formation. So it will perform the loop refinement again using prime. So the example is, you can see here there are two reactions, that is Michael addition and nucleophilic addition. So the change in hybridization can drastically affect the relative orientation of three functional groups, that is R1, R2 and R3. And that is the reason you need prime refinement strategies. Now, just to give you a pictorial view, so this is how it happens in glide, where the initial non-bonding docking happens, and then you perform your residue sampling, and then it gives you the final different poses. So you don't end up in single pose, you get different poses. In IFD also, you don't end up in single pose, you have multiple poses to check for consistency. And this is the whole protocol, how it performs. It performs the mutation in the reactive residue, that we call it as ALA scanning. It performs the ligand conformation with confusion. Glide is done with positional constraint docking, so that because it has to form a covalent bond, right? So you cannot give a lot of space to explore. Then apply the post-selection criteria. Then you have to the prime will do the rotamer sampling of attachment of bond formation, and it will cluster based upon the XYZ coordinates. Then you have, it performs the minimization of pose. Then glide will perform the scoring of the poses, and at the end you get the affinity score for the same. So you can see the number of poses that are refined, and you can say the number of poses to report. So by default, you may end up getting, and the whole process is automated, so you don't have to worry about it. So each process is properly calibrated and it is scored, so you get a best outcome. Now, think about this CoVDoc for your virtual screening. Now, the problem is, now the existing is computationally intensive and you won't be able to screen big databases. As I said, here it is kind of already predefined. Okay, this molecule is going to form, this is the reactive warhead of the protein, this is the reactive warhead of the ligand, and that is the reason the calculation takes tentatively in hours. Okay, but we have a separate, in the same GUI, we have a separate methodology called as CoVDoc VS, which is nothing but covalent docking virtual screening mode. And the calculation is not, this is lead optimization mode, this is virtual screening mode. So obviously it is going to take little less time than your normal lead optimization protocol. And I already explained you, and what are the steps it misses for your virtual screening mode. It does not have sample with conformation generation. It does not perform binding energy estimations. So those things are missing. So if you see clearly, the difference between lead optimization mode and virtual screening mode is like very clear, and that is the reason you get faster outcomes. So if you have a bigger database, then it is one among the best to use. So what are the validation case studies that are available? I have some interesting case studies. This was performed on 4 different receptors, and we have performed covalent docking to predict the RMSD of the binders, and we have used the decoy sets, and similar kind of reactive warhead was used. And when it was done, you could notice this is the potency range, and this is the actives, known actives, the number of decoys used. So the enrichment factor and bedrock score, you can see it's relatively better than your normal docking. So normal docking is not a solution, because if you notice, normal docking ends up in non-bonding interactions. So this is the enrichment graph, where you can see, like in most of the cases, within 30% of data set, it was able to screen out all the active molecules. So that is a concept of enrichment calculation. Enrichment calculation, nothing but mixing the most active molecules with decoy set of molecules, and then see how quickly the selectivity and specificity of picking up the molecule is there. Like within 5%, it was able to screen close to 95% of the molecules quickly. And that's what the data set is all about. Now, this is how the CoVDoc panel looks like. The covalent docking panel, this is the thing, as I said, though it involves a lot of science, and the option is quite self-explanatory to run for any no-voice user, and for advanced user, you have options to change. Okay, so this will be covered in the demo session in the later part, but for the time being, I'm just skipping this. Okay, so this is how the covalent docking panel looks like. You have to define the ligands with reactive warheads. You have to define the reactive residues, and then reaction types you need to define, and then you have to give the processor and here's that. Okay, so this will be covered in the second phase of your training session. So here I have shown you a docking output post, where you can see like how the different interactions, you have seen like close to 4 poses, and you get CDoc affinity score. Based upon that, you can say which molecule is better than the other. So this CDoc affinity score can be used for your screening, but individually you need to analyze what is the consistency of this pose and how to use it. So whenever you are working on any projects and you want to showcase, please highlight the covalent bond formation and different poses generated by covalent docking. So that looks nice, okay, because this kind of study is pretty difficult to do. So that's the reason you need to highlight all this. Now, moving forward, advanced methodology that is performed by FEP+. So that's a very nice paper. I will not give much detail here because it's a totally different topic, where it's a full benchmarking study, a collaboration between Schrodinger and Roche. In this, like they have shown how to design new molecules for cathepsin L inhibitors. It's a very nice study. I would request everyone to go through that if you're interested with how to use FEP+ for covalent binding design. Okay, and please understand that your covalent CoVDoc is used for screening of your molecule, but rank ordering of molecules can be done by using FEP+. And you can see how the binding modes and how the activity and new scaffold can be predicted using our FEP+. So this is for advanced and only for commercial, but at academic front, please keep in mind there is a method called as free energy perturbation available, and that also used for the designing of covalent inhibitors. I think that's all what I planned for today. I really thank my team and the organizer for giving this wonderful opportunity, and I'll be open for any questions, if any. Thank you.
Thank you for the presentation. We have a couple of questions. So there are some general questions and also some questions related to your presentation. So the first question is, what is the significance of halogen bond interaction?
Okay, maybe it is non-bonding, something that is related to. So that's also a kind of, if you see, there are so many interactions that contribute to binding. So halogen-based interactions are the one like which helps in your affinity, and it is easily, you can see, it's mostly involves your halogens. You can visualize it in Mastro, and it has a contributing towards affinity. So that is also available. So maybe I don't have slides now, but when you see the Mastro, there is a separate view for seeing the halogen bond interactions.
Can I add on, Vinod? If you
Yeah, please.
Yeah. So halogen interactions are very special type of interactions. Okay. Halogen interactions are weak type of interactions. So individual contribution could be less than 0.5 kilocalories. but these are special because they can offer all the types of interactions. So depending on the direction of approaching functional group, they would be able to engage whether it is electrostatic, whether it is electropositive or electronegative interaction, even the hydrophobic interaction they would be able to offer. So there is something called a sigma hole effect. These halogens will have sigma hole effect. That means there would be a charge separation. So if any functional group is approaching from the front directly at 180-degree angle, then it would offer electropositive interaction with them. So just behind the electropositive band, there would be an electronegative band. So let's say around 140, 160-degree angle, if some functional group is approaching, then it would be able to offer a electronegative band. And behind that, it is all, everything is hydrophobic. So that is why these are very unique. And this sigma hole effect is very unique to individual halogen. So if you consider the largest halogen, that is iodine. So here the sigma hole effect is very strong. The charge separation is very strong, followed by bromine, followed by chlorine. But fluorine doesn't follow this rule because it is highly electronegative. The charge separation doesn't happen. Sigma hole effect is not there. So because of this type of uniqueness, the special property, like it is able to offer all the type of interaction, they are very special. Thank you.
All right, moving on to the second question. So what is the difference between protein preparation wizard and prime refinement?
Okay, so if you notice, the prime refinement involves loop sampling, where it generates the various conformers of the loops in the binding site. And the same concept is used. There are options for sidechain refinement also, but protein preparation has limited options to save the integrity of your native structure, native crystal structure. But this need to be explored when we are performing lead optimization step. Is it okay?
Yeah. So the next question is, what value of RMSD can be considered a good one while comparing the docking results?
Okay. See, please keep in mind, docking is actually, so now I have seen many researchers are so much behind these values. So you need to cross check. There is nothing good or bad. It is, for example, as less is obviously required. Like for example, if the RMSD value is close to 0, that means there is no change. But now you got RMSD of 3. You need to explore why it happened. What is the reason behind that? Like for example, if I perform a molecular docking of flexible protein, then see, obviously it improved. So molecular docking obviously will not be able to give me better RMSD because I have to use a different approach. Please think about why you're getting higher divisions. Higher value is always not nice, but you have to explore. So it is not about right, wrong, good, bad. No. So this is the research outcome. What is the reason why you got this? So that you need to explore as a researcher. Is it fine? So close to 0 is what is preferred.
Thank you. So the next question is, so we have performed XP docking followed by MD, and then we select ligands having good D score. Can we or should we perform IFD on these ligands?
No. Come again.
So we have done a docking followed by MD simulation.
Okay.
Then we select ligands with good score, with good docking score. Should we perform IFD on these ligands?
Okay, so that is the reason I said, clearly I said that maybe you have a luxury of excellent hardware. Okay, so that is the reason you immediately switch to MD. There is no problem of going into MD, but you know the loop movements in an MD takes larger simulation time. Okay, so now you have already done MD, and if you try to analyze the flexibility in the binding site, then you will get to know whether are you getting any major flexibility or not. So it is not a compulsion. Obviously, molecular dynamics approach is much better. So IFD, like whether to use it or not, it will be decided based upon your enrichment. You have to perform some enrichment calculation on your stable pose of your MD. If you're able to get better enrichment, then you don't have to do that. You don't have to come back to IFD. If it is not able to stabilize your complex and not able to pick your active molecules properly, then you can try IFD and followed by an MD to stabilize it, or only IFD alone. You can check how the enrichment is. So see, any validation is significant with the experimental outcome. So whatever experimental has proved as active, the in silico, we need to see what are the different ways or which approaches I have to use for getting better enrichment. If docking itself is going to help me with that, then I'll stick to that. Is it okay?
Yes. Moving on to the next question, is it possible to calculate K of for bound drug molecules?
Come again?
Is it possible to calculate the K of value for the bound drug molecules using Schrodinger, the dissociation constant?
I think it's not a direct approach, but there is. I have not done it personally, so maybe I have to check and get back, and I'll see, and I can answer because I've not worked on calculating the K of values and all that. I'm sorry.
Sure. So the person can just write to us. If there's a way, we will suggest it. The second question, next question is, does every molecule has an ability to form covalent bond?
I think I clearly said it's a matrimony of reactive warheads of the receptor. Okay, the receptor should have the tendency, and the molecule should have the tendency of reactive warheads. And I think that could be like, so when this matches, then the covalent bond formation is possible. And that could be also be a reason like maybe some toxicities are come out because that angle is never explored. So maybe like it's not the case with every molecule, but it has to find the right receptor or right partner. Then there is a possibility of formation of covalent bond.
Right. So now there is a general and very interesting question. So the person's asking, so even though we have learned how to use this software, do we need the whole pharmacological knowledge to be able to be productive in drug design?
So this is a multidisciplinary field. Personally, I'll tell you, nobody can become an expert. And one day you have to note down what are your plus and minus and what is your objective. Like for example, if I'm a student, I'll think about what is the plus and minus I have, what are the things I can do and not do. And obviously the world will recognize. So as you slowly move around and understand your drawbacks and improvise on it, so your scope of improvement happens. But so there is never like your valence electrons are full. So though we are in industry, still we need to learn. We have to update ourselves in every situation. So as a student, as an initial career, note down what are your positives and negatives and see what you know and what you don't know. And slowly you explore because we are too rigid with our domain. So we never want to come out of our comfort zone. And that is the major reason for all these talks. Is it fine?
Yeah, thank you for that answer. So the next question I'm reading as it is. I have learned that covalent docking has the biggest demerit that is off-target reactivity. So how do you justify this demerit of covalent docking?
Okay, so let me tell you. See, it's a receptor, the project, and everything. Okay, now it's a topic of debate. Like, okay, off target. If you want, you can go ahead with that. So whatever the off target, I don't want because I don't want it to end up in a side effects or adverse effect. So for your project, if you need off target reactivity, obviously you should do it. I have never said like, okay, I mean to say as a general case But as you're saying, you have learned it, so obviously you should use it. So there is nothing a debate like, okay, yes, it's your thought. Being a researcher, it's your project. So you should to decide whether you would like to have the off-target reactivity or not. But the covalent inhibitor are cautiously held. And that is the reason, though we have close to 1,500 drug molecules, there are very less covalent inhibitor which are very nicely druggable. And many of the researchers don't focus on that also. So it requires a lot of research to claim any statement. So I don't want to claim that, but yes, it's everybody opinion, individual opinions. Is it okay? Hello, Sylvia. Sylvia, are you there? Any problem?
Yeah, it's okay. Let me take the next question. What is ensemble docking?
Okay, great. So ensemble docking is nothing but when we try to take different conformation of the protein ligand complex that is generated by induced fit docking. I should have put a slide for that, but I'm sorry, but nothing else. It is like now the various poses that is generated by IFD or molecular dynamics. When you perform multiple docking on all these receptors and see the consistency of pose would be termed as ensemble docking.
Thanks, Vinod. The next question is, in covalent docking, is the protocol the same as regular docking, or is there a difference in the protocol?
I think I clearly told that it uses the knowledge of molecular docking, but it has combination of loop refinements. And it does van der Waals scaling, and it does ALA scanning on the reactor for providing the flexibility and recalculates the energy. So you can say that it's a hybrid of molecular docking.
Okay, thank you. And the next question is on FEP plus. It's a name of an algorithm. So the question is not clear to me. Maybe you can try to understand what is being
So
asked.
FEP plus is a methodology like molecular docking. FEP plus is a free energy perturbation. OPLS 3E is a force field name. Like you can say there was OPLS 2005 or Merck molecular force field and so on. So it's not an algorithm. It's a product.
Is there a distinct tool set for FEP implementation during docking?
Yes, we have, but it's majorly used for commercials.
Yeah. Just to add to that, if you have the computing power, you can use it as well. FEP plus requires a lot of computing power. Even in academic labs, you can still do it if you have access to a lot of GPUs. I think we have probably two more questions. The first one is, after doing covalent docking, can we identify the off-target reactivity? You probably touched on this, but maybe you can just elaborate on it again.
No, come again, what you said?
Can we identify off-target reactivity for covalent docking?
No, see, this is, if you see the whole protocol off-target effect, you need to explore on different receptors. So like, for example, now I have a receptor A, I will get to know whether the covalent binding among these 10, 20 molecules, whether it is good or bad. But if I have to explore on other targets, I have to see what is the mechanism. So immediately the covalent docking will not give you the off-target outcomes. It is going to tell which molecule is going to be good as a covalent inhibitor against that receptor.
Right. I think this should be the last question. How to modify the functional group of a particular ligand or inhibitor and check the potency of a given inhibitor against a target receptor.
Okay, so the fact is that obviously now everybody, this is like a very broad question, how to modify. And that is the reason we have this many tools. And the check the potency is like either done in silico and then. So now in silico work is going to shorten your list of active molecule, means the molecule for testing, to safeguard your time and efforts. So now that is everybody is thinking like which functional group have to modify. There are various methodologies like 3D QSAR or pharmacophore modeling, or you can see molecular docking. So these are different approaches where you can define, okay, which group is good, bad, and test your hypothesis in silico and take the best possible molecule for your wet labs. Ultimately,
Yeah, Yeah, thanks, Vinod. We got two more questions. The first one is, if the protein has multiple covalent modification sites, can we go sequential covalent docking of the same receptor with one or more ligands?
So you can't do like it can't perform simultaneously on both sides. It is nice to explore. It's a very good question, which I was thinking to some research need to come out. Like for example, there are two cysteine in the binding site. You don't know which one is the dominant one of forming a covalent bond, and so you have to perform like QMMM calculation there to see like which residue has higher probability of forming a covalent bond, or comparatively do both this docking on both the side and see which one has higher tendency of forming a covalent bond. It's a nice topic of research. I would love to do it, but currently it is in pipeline. Like, let
I
us
think the
see.
question is more related to having multiple ligands on the same receptor.
Yeah, I
And
got it, but it's not possible.
yeah,
Can't do two simultaneously. Can't do. But if it is like if the topic, the same question I'm rephrasing. For example, in a single site, if you have two residues that has tendencies of forming the covalent bond, and you don't know like which it is going to form, that's a nice topic of research.
yeah. We are still getting some more questions. So one of them is there a distinct tool set for dealing with custom-made small peptides as ligands, or are they treated as any other small molecule ligand?
No, peptides, we have a separate treatment with biologic suit. Peptides are very tricky in nature. As the length of the peptide increases, getting the conformation sampling of them is very tricky. So we have so many conformation methodologies that you can use. So that is there in biologics, peptide docking options are there. So it's not treated the same way like organic molecules, but it can be treated like same as organic molecule. So currently, like everybody is using the same approach, but if you're quite cautious, you have to do some benchmarking studies on okay, which approach I have to use, and some of the approaches are already made as a tool and available in biologic suits.
Yeah. Thanks, Vinod. There is one more question on the comparison between Autodoc and Schrodinger. How do you compare the results between the two softwares, and which one is better?
Okay, see, there it is like it's like a knife. So obviously, Schrodinger is a commercial company, and Autodoc is an open source tool. If you know the science, it's very easy, especially for those who don't have much exposure. I'll suggest understand in a commercial software how it is done, and see the drawbacks and pitfalls. If you're able to fix all that in an open source, it's well and good. But our we don't get that much time to explore all this. But yeah, but you have to know like how to use it. It's very easy with Schrodinger, but whereas with Autotalk it's very difficult. And accuracy level, I will suggest like it depends upon the user. And in major, the way the program and modules have been made is well validated and used in industry. So we should not have the attitude of a publication-based approach. But in industry, like if you see majorly, they use Schrodinger software. Why? Because of the reproducibility and the consistency of the results. But with Autodoc, it's very tricky and very difficult.
Thanks, Vinod. I think those are the questions for you. There is one question from Debaditya. Will there be a session covering biologics module? Yes, we have a session for biologics on September 30th.
Yes.
And I think Shailya will have announcements regarding the rest of the course shortly, and also regarding free version of the software that you can try out. It's over to you, Shailya.
Thank you, Kaushik. Thank you, Shalvia.
Thank you. And thank you, Kaushik, for taking up the questions. Yes, some of the announcements that I promised in the beginning. We have put together a form for you if you are interested in taking an evaluation license. Since we are starting the demo sessions shortly, so it will obviously be helpful if you have a copy of Schrodinger software on your computer. So we will be sending out emails. The email will be sent to you by ddcourse@schrodinger.com. So by tonight or by tomorrow 8 a.m. you will be receiving emails. Please keep checking your spam as well, because sometime when we send bulk emails, it might end up in your spam or in promotional emails. So please make sure that you check those sections of your emails as well. Or you can just search for any email by ddcourse@schrodinger.com. So you will be receiving this email by tomorrow morning or by tonight. So if you don't receive it, only then you write to us tomorrow. Other than that, just please check your emails. Usually everybody receives it. There's our scripts are very well validated, they go everywhere. So it is possible that you might see them not in your inbox but in your spam or promotional emails. Please check that before writing to us. We are getting a lot of queries and we like to answer all the queries, but sometimes we are not able to handle all of them because we are a small team here in Schrodinger. Please make sure you check all that before writing to us. And if you don't get it, maybe you haven't registered. So please go to our website, www.schrodinger.com/dd course. That is the short URL for this webinar series. So please go there and register yourself if you haven't already. There will be a section in the form which requires you to tell us what hardware you have. And if you do not have the required hardware, it is not optimal for our software. So we will not be providing evaluation for you. There are some hardware that do not match the optimal ones. So there is a section where we ask you to write down your system configuration. So please send us that so that we can check and make sure that we are able to send out licenses to everybody who can use it. We really want you to use our software, and it will be very helpful for you for the demo sessions. The second announcement that I want to make is about the SOC, the Schrodinger online course. So when do you take this Schrodinger online course is when you do not have the hardware, as well as if you want to have a separate course. It's a certified course. You get a certificate out of this course when you finish it. So if you do not have hardware, this is another option for you. You can write to me. There will be another form for this. So whoever is interested can let us know if you're interested, and we are working out on the deal, like how much it will cost you. And if there are more people, we can get a better deal for you. So you will be getting a form for that. Please fill out if you're interested. So it is not necessary that you either go for the evaluation or the SOC. You can opt for SOC even though you are going for evaluation, because SOC has a nice self-paced course that you can take whenever you're free. It takes about 24 hours to complete the entire course. It is also followed by a case study, so you will be able to work on a case study at the end of it. Also, after the completion of this course, you'll be receiving a certificate by Schrodinger and a badge, and also you'll be a part of the alumni page on our LinkedIn. So those are some of the advantages of SOC. The other thing is, do not wait for these forms to come to you. You can just go to our website and request an account. So if you go to schrodinger.com/request-account, there's a small form which is not same as the registration for this course. Okay, that is separate. So you need to register for this course at schrodinger.com/dd course, this website, and you have to request an account on Schrodinger website, which is here. So this is schrodinger.com/request account. There's a small form there. Please make sure that you put your institutional email if you have that, because that we can get your account activated much faster if you put the institutional email. So make sure if you have that, please mention that instead of using your Gmails and Hotmails. So please do not use that if you have the institutional emails. If you do not have them, you can give that, but make sure you put in all your details. So you will have to put in the company, means the university institution you are part of. Please make sure you mention all these information clearly, because if you do not mention it, your account will not be activated, and our team will be asking you questions about these details anyway, so it will be a long process if you do not do that. So make sure you keep all the details with you, and you fill out all your details there. Other than that, I don't think I have any more announcements. We will be sending out the email, so please look out for the email today or tomorrow. If you do not receive it, make sure you register today if you haven't done it, and if you don't receive it, you can write to us after tomorrow. We will look into it if you haven't received it, and we can send you the form ourselves. So I think we are done for today. I would like to thank you for attending these lectures. Please, as I told before, make sure that you attend them in person live, so that we can help you with your queries and we can answer all your questions. We also have office hours every Thursday from 4:30 p.m. to 5:30 p.m. Indian Standard Time. So if you are not able to attend the live lectures, or if you have some questions that you were not able to ask during the live sessions, and you would like to ask them in the Q&A or the office hours, you can please join us via the Zoom link that we have sent to you through emails. So if you haven't received it, please write to us and we will send it to you. I think that is all for today. Thank you for attending. Thank you for submitting your questions. I would like to thank all the panelists who are here to support us, and the JSS IT team and the Manipal team, where these lectures will also be hosted. So thank you and have a great day. Bye-bye.
Sir, live feed can be stopped. Dhananjay sir, are you there? The live feed can be stopped now.